Alrighty. Number of subsequences that satisfy the given sum condition. Medium. Okay. You're given an integer array and a target integer. Return the number of non-empty subsequence of nums such that the sum of the minimum and maximum element of it is less than or equal to target. Since the answer may be large, return it modulo 10 to the 9th plus 7. Okay, so example, if I have 3, 5, 6, 7, target is 9, the low could be 3 and the high could be 6. So it could be 3, 6, but also it'd be 3, 5, 6, I assume, because that's also a subsequence. Can't have 7 because that would change the high. So those two, and then what else? There's 4 answers. Min and max value target. Oh, it's less than or equal to target rather than just equal to target. Okay. So it could be 3, it could be 3, 5, it could be 3, 5, 6, it could be 3, 3, 3, 5, 3, 5, 6, or 3, 6. Okay. Target is 10, so it could be 3 by itself, 3, 3, 3, 6, 3, 3, 6, 3. Oh, interesting. It could be literally the same value but different indices, so it makes it a different element. Oof, that's gonna be. I guess that might be fine in terms of what it does. Interesting. So how to go about this? Values are all positive. 1 up to 10 to the 6th power. I guess it could possibly be empty as well. Return the number of, so it could be 0, I think. Can I do sliding window? I think probably sliding window is the technique I want to use here. And then I keep track of the min and max of the window. So let's carefully consider the first. Can I somehow figure out how to deduce the 4 outcomes here? So the smallest is 3. So I start at 3. And then I extend out the window. Actually, how long is this? 10 to the 5th, so it has to be something that 10 to the 5th, so it has to be something that's not n squared. I think maybe I can sort this. I'm pretty sure I can sort this. Yeah. Because order doesn't matter. It could be 3, 5, 6, 3, 6, 5. The values themselves are what's important. So I think I can and should sort this. So num is not sort. So answer is initially 0 is the count. So for each number, so if it's 3, 5, 6, 7, and the target is 9, then 3 can go up to 6. And any subsequence that starts with 3, that includes 3, that includes this 3, and the number of subsequences that can go up to the 6. So it could be the 3 and the 5, it could be 3, 5, 6, or 3 and the 6. 3, 5, 6. Or it could be 3 itself, right? 3. And then because 5 cannot, if 5 is the minimum, then it cannot go anywhere. Like, there's no other, well, 5 by itself could work, right? No, 5 by itself couldn't work because 3 would be, 5 would be the minimum, 5 would be the maximum. Okay, so maybe something like that. And then if it was like 3, 3, 6, 8 sorted, and the target's 10, then the first 3 could go up to the 6, which makes it 3, 3, 3, 3, 6, and then 3, 3, 6. And then the second 3 could go up to the 6. So that second 3 is 3, and that second 3 could go to 6. And then the 6 can't go anywhere. So that gives me 6. Okay. So is there a formula for the number of subarrays or subsequences that I can form from a given start index to a given end index? So that's really the key part. So for a given start index, number of count of subsequences or given start index to end index in sorted array. Is it well, if you include things, it could be it, but so if I say like 1 is inclusive of the index and 0 is not inclusive, then it's like a 1 followed a bunch of zeros for whether or not it, and that kind of means that the first thing is included, which is always necessary. This thing's always necessarily 1, but then the remaining stuff could all be not there, or could be mostly, or one of it's there. So I feel like this portion is going to be 2 to the n minus 1, where n is like maybe the number of indices minus 1. Minus 1 because you can't actually have, no, it's actually 2 to the n minus 1. Why is that? Why is it minus 1? It's just 2 to the n. It's 2 to the n, this should mean that all zeros should be part of it, no? All zeros being not including the first part. So if it's not 2 to the n, then why is this? If this is 2 to the n, this should be power of 2. So I'm missing something. No, okay, I see it. So, I see. So the number of subarrays or subsequences that exclude or not counting the first part, because the first one has to be inclusive or has to be there, so it has to be a 1 starting with a binary string. But then the other ones, they can't be this stuff. All the values that this could be would be 2 to the n. Okay. Okay, it's 2 to the n minus 1 because I can't actually, well, this is basically having zeros, right? Okay, yeah, this is basically having zeros. 1 followed by a bunch of zeros. Wait. what is going on here? Okay, so if it's just 3 indices, it's 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. There's 4. So what is going on? So these are the 3 that I see. These are the 3 I see, and the empty one is equivalent to the singleton. Okay, so it's 2 to the n. It took me too long to figure out. So basically, if I take the difference between the start and end index, 2 to the power of that difference should be the number of subsequences that can start with a certain index. Okay, so then is there a faster way of doing this? No, I think sliding window is correct here. Okay, so this is going to be sliding window technique. So for any start index representing the min value, extend out the right window, right side of the window, right, the start index, which is start / the left side of the window, left index. Send out the right index representing the inclusive max value. Any subsequence that has the min value and any number of values up to the max value, or in this case, specifically the indices. Is a valid subsequence for the answer. So, and the number count of subsequences for given where min and where indices with indices from I to j, inclusive of I and inclusive of j, would be 2 to the power of j minus I. Okay. So let's say for every left index, actually I'm going to start with saying the right index is going to be 0, and I'll have n as the length of the number of indices. For every left index in the range of n, I'll say while right is less than n and nums at left plus nums at right is less than or equal to target right. Actually, let me think about this. So the first thing, 3 matches with 6, and then 5 matches with something less than 6, right? 5 matches with 5 can't even match with anything. 5 matches with itself, really. So it only decreases the right side bound. So the right side bound goes leftwards. How's this? Okay. I think maybe I need to have initial right bound. That's as far as possible. Okay, so the smallest value Let's see, I'll say right is equal to 0 while right is less than n and num's at 0 plus num's, actually I should be n minus 1, so let me go backwards. While num's at 0 plus num's at right is bigger than target, then right minus equals 1. So you assume that maybe you have all the subsequences, so like 3 all the way to 7 as your bounds. That doesn't work because it's bigger than target when you add 3 and 7, so therefore you go backwards 3, 6, that works. That stops. So while right is greater than 0, greater than or equal to 0, greater than 0, greater than or equal to 0. Okay, so you stop there, and then for every left in the range of n, I think you still have the while loop here. While right is greater than or equal to, I think this one should be greater than or equal to left, and nums at left is plus nums at right is greater than target, right decrements. And then answer plus equals, this could be false. This could be something where it ends up being that there is nothing. Like right actually goes past left. So when like right is, left is 5, right actually goes up back to 5 plus 5 is going to be greater than target, so right actually goes back to 0, index 0. I think I can say here if the right is less than the left, then break. Otherwise, increment the answer by the number of subsequences, which is 2 to the power of, our answer equals 2 to the power of right minus left, and then mod, and then return the answer. Alright, let's see how this goes. Okay. Not bad to pass the test cases. Okay, well, it goes very slowly. So there's answers in my vicinity, or solutions that are on this order of magnitude, and then there's solutions that are efficient, extremely efficient. Or much more efficient than my solution. So start with the smallest. Why would this be so slow? There's 61 not empty. So how fast is it doing these? I mean, is the array already sorted? No, the array is not already sorted. Even though these test cases have all sorted arrays. So I'm pretty sure I need to sort initially if this is the thing I'm trying for. Since the answer may be too large. Not sure why it actually is so slow. Seems like it'd be pretty darn fast. So you sort it, you figure out what the rightmost bound window is. And then you go and then you do the main loop, which is going to go through every value and verify that the bounds are still fine. If not, change the right bound. Ooh. And then increment the answer. To 2 to the power of right minus left. Is there some other facet of a sorted array that I should be leveraging? Is there another facet? So I go 3, I figure out 7 doesn't work, 6 does work. Figure out the length that 3 to 6 is 2. That gives 3 subsequences. And then I move on to say 5. 5 is bigger than 6, or 5 is not. 5 out of a 6 is not going to be okay. So 6 goes down until it is. I mean, I guess I could do a search of the, instead of doing a while loop to find the appropriate spot of the right thing, I could do a search for, no, that doesn't work either. What does it? I could search for the index that I would find the complement to be. So 3 complementary value to get to target 9 is 6, so I can use bisect left to find where 6 is within the sorted array, rather than use a while loop. I guess that's pretty fast. Okay, so I say right is going to be bisect left of target. This is always going to work. Target minus the low value nums of 0. So let's think about what if the numbers are too big. What would happen? If numbers are too big, then like it's not possible, then you would insert, then the right would be before the left index. The right index would be at least 0. Okay, yeah. So I find it using search for the right index, and then for every, actually I could probably do that. I could probably do that for the main loop. I don't need to do that outside the main loop. So the value is equal to nums at left. The complementary value is going to be target minus this value, and then the right index is going to be equal to bisect left. Bisect left searches for it within a binary. Or actually, I need to specify the array and then the value. And then if the right, I guess if they're at the same index, if the right is less than or equal to the left, then that means less than or equal to or just less than. If I'm at 5 and 5's at index 0, if I'm at 3 and 3 is index 0, I'm searching for 6, and the next thing is 4. The next thing is, let's say, 7. So inserting 6 would be after it. Yeah, it's always going to be fine if it's after, but if it's equal to, then it's trying to insert it before it because it's smaller. And I think break is here. Answer equals answer plus 2 times the power of right minus left. And then right minus left in parentheses. Modded. Okay, let's see if this one still works. Works for one of the cases, does not work for the other cases. Huh. Answer is too big. Let's see, 2. Alright, let's go and just do some printouts here. Print the value, print the comp, print the left, print the right. Okay, so wait, what? Okay, so this one, the answer should be 6. So it should be 3 going up to 6. So 0 goes to 3. 0, oh, I see. It's off by 1, I think. Because you're inserting, you're trying to find where, shucks. You're trying to find where the complement plus 1 is, I think. Yes, complement is plus 1. Because the complement is fine. And then that changes the right index. So I think complement plus 1. So your range includes, your range now includes, it's inclusive of the thing that you don't want to have, so it's minus 1. Okay, yeah. So that issue was if I said 3 is the current value and 6 is the complementary value that I need to find in order to add to 9. I want to find where not 6 would appear in the array, but where 7 would appear in the array. Because 7 is after all the 6's that might appear in the array. And 7 is the non-inclusive index that I want to end the subsequences with. Because I want to include all the 6's. So, and if you do bisect left finds where you insert the first 6 rather than the last 6, kind of. So it would find this index between the 5 and the 6. And then you technically don't include the 6's, so you have to do complement plus 1 as the complementary value plus 1. Alright, so I think I can see how this goes. This should be faster, considerably faster, fairly faster. Should cut down the gap between me and the other solutions. No, not at all, really. The gap is enormous. The gulf is wide. What am I doing that, what am I missing here? Break out early. I guess I could say I bisect left starting at the left side index. So whatever the left index is, in that case, if right is equal to left at that point. So bisect left has a third parameter or third, fourth parameter where you specify the indices that you're searching through. So I need to search through anything after left rather than anything before left, because then that's just impossible. I don't think this makes much of a difference. It makes zero difference because binary search is like too fast for this to make a difference, I think. But it's a slight optimization. I mean, you can preload the powers of 2's rather than recalculate powers of 2 each time. So you have an index that is powers of 2. I wonder how slow this operation is actually. If I say powers of 2 is an array, and how big do I need this array to be? There's some maximal size to the array. There's some maximal size to the array. And so I could say if not powers of 2, then create the initial size, then for every p in the range of right minus left minus 1, right minus left, then powers of 2, let me go ahead and say the first powers of 2 should be size 1, 2 to 0 is 1. And then the next one would be 2 times the next element. I guess this should be append because it's not going to be the correct sizing. Powers of 2, the last element of it, times 2. Okay. And then I can just use the array. Powers of 2 indexed at right minus left minus 1. Right minus left could be, let's see, right minus left could be, let's say initially 5. So I append 1, right minus left could be, okay, I think this is fine. Powers of 2 append, powers of 2, powers of 2. Okay, see if having some pre-calculated powers changed anything. Okay, so it did change some things. So the drop off between this thing to this thing, which was like 6 milliseconds, or 6,000 milliseconds, which is 6 seconds versus like 1 second, was not calculating these powers of 2 each time, but having an array of stored values for those. That's not enough. There's still some other optimization I can do here. I think this is deletable at this point. Yeah. So you extend out the rightmost window. So 6 goes to 3. Am I doing this the wrong direction actually? So I can go if I go the largest possible, if I go backwards, 6 goes all the way to 3. It should always be possible to go to the smallest, right? And then 5 should always go to 3, and 4 goes to 3, and 3 goes to 3, and 2 goes to 3. So anything that is 6 to 3, any subarray, any end index that is smaller than that can go to 3. Oh, maybe I'm just thinking about this wrong. So if you think about where the smallest is, I think about where the smallest is. So that's going to be powers of 2. Uh, 6 goes to 3, 5 goes to 3, 4 goes to 3, 3 goes to 3. Because I would always want to include, yeah, I would always really want to extend to this front if I go backwards. If I go starting from 7, 7 would try to go to 3, because that just makes it smaller. I think. No, I might think about this wrong. If I have 6 as my endpoint, then you're inclusive of the high value. The high value would always extend fully to the lowest value. Yeah. So what does that mean? That means you don't need to find, if you're going from the right side, you're always extending it to the left side. But then if you know where your right side is, then you're doing a for loop from your right side to your left side. Okay, let me think. So let's say the target here is 20 or 120, it's fine. So you're doing all of it pretty much. So you're doing 3, 3, 6, 8, and then you're doing 3, 3, 6, and then 3, 3, and then 3. So this is 8. Is your answer always like a sum of powers of 2? 4 plus... that's really not a sum powers 2. Is it always a power 2? No. So this is going to be 16. This is going to be 8. How is 3 to 3, 4? This should be 2, right? 3 by itself, or 3 with a 3. Zero, 1, 2, 3. Should be 8, 4, 2, 1. I'm missing the pattern here. 3, 3, 5, 3, 5, 6, 3, 6. Okay, I Yeah, I'm thinking that was wrong. The number by itself can't always work. If you go backwards, the number by itself, you can't just say 7 is going to work. Because the number by itself would make it the low and the high, and that wouldn't work. Yeah, it makes more sense to go from the low, I think. From the low, you can say the low by itself would be the low and the high. And then you're just extending out how far the high could be. I guess there's probably another way of doing it where it's going backwards. Like you start by saying the high and you figure out where the low should be. What the low should be, and then figure out where the low can be found. Yeah, they're pretty equivalent. It's just the logic is that it's not any less than the current logic. Am I satisfied with this middle 45% answer? I guess my question is like, how is this gonna be faster, or where the speed increase can be found? So this seems pretty darn fast. This seems, oh, this is n log n. And if it's like something that the answer is 120 milliseconds, that might be like n speed. So somehow they sorted it and immediately got the answer, or they didn't even sort it, they just do a linear approach to it. We did a linear approach to it. Interesting. So if you do, can you do a linear approach? So if you didn't sort and just had 4 random numbers, or 4 unordered numbers, 3, 7, 5, 6. If for this number you counted the number of other numbers that are smaller than 7, no. Go through the rest of the list, and you see the number of other numbers that add up to something smaller than 9. Yeah, I feel like you need a sort. Alright, I'm going to go ahead and look at hints here. Sort. Use 2 pointers approach. Yeah, 2 pointers being something you kind of need left and right for. Count the numbers. Okay. Okay, I'm gonna take a peek at what might be faster than me. And oh, interesting. So instead of appending just the powers of 2, since these can be big, they appended powers of 2 mod the constant. Yeah, so this is percent mod here. And at that point, I think you still want to do mod here. Is that really the thing? That was the thing. Well, that could have been a hint, but I guess I had to resort to actually looking at other solutions in order to find it. But I think I'm satisfied that I did pretty well up to that point. Okay, so going through the ending here. Summary, this is going to be, I'm going to call this, I guess it's really not a sliding window at this point, but key point is to understand, key point is to recognize that for a given min value, any subsequence up to the max value of a sorted array where min is valid. So steps would be to sort array, iterate over min values, particularly the min indices, really. The indices that you want to treat as your min. Indices to use as min. Indices to use. Indices of min. And then find max value such that min plus max is less than or equal to the target. Use bisect. This is really kind of an optimization. Use bisect left to identify where last max value is found. In this case, it'd be bisect left of the array and then the complementary value plus 1, where comp is equal to target minus the min value. And then increment answer by the number of subsequences between min and max, and this is going to be 2 to the power, 2 to approximate power of the difference between those two. And then the optimizations would be to have an array of values for powers of 2. So to make calculations for part 5 to use stored values rather than calculating powers of 2 each time. And then further optimization is optimization is use mod in the powers array rather than just at the answer increment, since powers can be very big. I got to everything besides step 7 without help. Alright, time complexity, this is going to be O of n log n to sort the array, O of p to create the powers array, where p is at most n the number of differences between the right and left index, and O of n to find see O of n log O of n log n I think it might be O of n for the main loop to calculate counts. We are iterating through all the valid indices of left. Technically the right calculation here is log n, but it's faster this way than bisect left nums of comp left. I think this should be left comma right actually. Maybe that actually speeds it up, because the bounds of the search should be smaller each time. I guess right should initially be n. Where n is the length of nums. I thought I defined n. Oh, I guess I delete too much here. What did I delete? Oh shit. Right equals n, where n is equal to length of nums. Oh, whoops, I defined it right afterwards. Whoops. I'm a little confused because this in theory should be faster using bounds on a search, binary search, than going through all the values. But going through all the values is at most n as well. I don't know. Space complexity, this is going to be O of what? O of P to have stored values for powers of 2. Everything else is fine. Everything else is the same. Alright.